Welcome to the 47th lecture in this series. So towards the end of the last lecture, we had constructed a basis for the space of multilinear maps to R in terms of the dual basis of the underlying vector spaces. We will talk about some general properties before I move on, so I should remark that the construction of the basis showed that the space of multilinear maps from V1 up to Vk to R is actually just the dimension of V1 multiplied by dimension of V2, etc. It's a product of the dimensions of the underlying vector spaces. So as an example of this, so let us see. So let's try to express, now that we know that these tensor products of one form a basis, we can try to express some familiar multilinear forms in terms of the basis. For instance, in Rn, let's take f of Vw to be the inner product of Vw, which we talked about earlier. This is a bilinear form on Rn. So So I can start with any basis of Rn, denote the dual basis. Earlier I denoted it by omega1, omega n. Now I'll just put a star. Dual basis by this. We know that by the theorem I can write f as summation aij vi star tensor vj star. Right, so here this ij equal to 1 to n. So in general, so this is the best one can, if for an arbitrary basis, this is all one can say. I mean, I really can't use the fact that I'm working with the inner product to say anything more specific. But let's say so this is for some aij in R. The point is, what are these aij's? So as I said, in general, for a general basis, there's not much which can be said. One can say something, which is that since actually the proof gave us exactly what these aij's were. They were obtained by evaluating f on the corresponding basis vectors, f where. So in fact, aij equal to f vi vj. Now since this is the inner product, we started with the inner product, the standard inner product on Rn. We know that we can switch Vj and Vi, and so this is Vj Vi. But f Vj Vi is Aj, the coefficient Aj. So what we can say a certain few things, namely that Aij equal to Aj for all I and j. And moreover, also if V is not equal to 0, F, since it's an inner product, FVV is greater than 0. So this is just inner product of V with itself is greater than 0. But if we write, if V equals, let's say, C1 V1 plus Cn Vn, then I can, this FVV, as we had done earlier, we can expand it in terms of this is equal to Ci Cj Fvi Vj summation over Inj, which is the same as summation over Ij Ci Cj Aij. So the point is that this is greater than 0 since this is FVV, and this should hold, this inequality should hold for all C1, C2, Cn not equal to 0, not the 0 vector. So as long as these coefficients are not 0, in other words, I started with the assumption V is not equal to 0. That's the same thing as saying the coefficients are not 0. So therefore, I have this. Well, so this inequality here is something familiar, which arises when one studies matrices. So if A equal to the matrix given by the coefficients Aij, in other words, A11, A1n, An1, Ann, and if we write C as a column vector instead of a n tuple like this, Cn, then this inequality star just tells us that look at A times C this vector C, column vector C, then multiply by C transpose. When I do A times C, let's just check it. So A times C is A11, A1n, An1, Ann. This multiplied by C is the column vector given by A11 C1 plus A1n Cn, An1 C1 plus Ann Cn. And if I do a further, so this is AC. C transpose AC would be AC equals, so C trans C1 Cn, now it becomes a row vector multiplied by this column vector here, and that will be, well, A11 C1 squared plus A12 C1 C2. Actually, it's just a number. I don't even have to put this bracket, etc. plus dot dot dot. So Aij Ci Cj is what essentially what one gets, Ci Cj. So this is this thing here, what I have here is just saying that C transpose AC is greater than 0 for all C not equal to 0. In other words, this Aij matrix, where Aij is F, the inner product of Vi Vj, is a positive definite, and here we had symmetric. It's a symmetric positive definite matrix. So and in fact the converse is also true. If I start with a symmetric positive definite matrix, I can define a bilinear form by this prescription here, and I can define F by this formula here. Then one can check that F is an inner product in the sense that it's a bilinear form which is positive definite, which has the usual the properties of the usual inner product. Well, that is one thing. But let's if we choose. So here I started with an arbitrary basis V1, V2, Vn. However, if I start with if V1, V2, Vn is an orthonormal basis, then this inner product just becomes, well, again one is working with the same formula, but except that now Aij, which is Fvi Vj, would be, if I is not equal to j, this inner product would be 0. If I equals j, the inner product would be 1. So one would just end up with V1 star tensor V1 star plus Vn star tensor Vn star. Right. Now the second example is, let's look at on R2. In the case of R2, bilinear forms on R2. So the determinant as a function from R2 cross R2 to R. So let's try to express. So this is my F. Again, I would want to express F. So here, let's start with for instance, I can have the standard basis E1, E2 denote the standard basis. Of R2. Now I would like to express this F as, we want to write F as, so yeah, and again the E1 star E2 star dual basis. So I know that F can be written as Aij, Eij star tensor Ei tensor Ej star. So I summation over Ij. So one wants to find out what these coefficients Aij are in this case, for the case of the determinant. So we again go through the same process. So Aij is just given by f of Ei Ej, which is determinant of the matrix given by E1, Ei Ej, where I write Ei, as usual, these are written as column vectors. Now, if I equals j, then these two columns will be the same, determinant is 0. So, Aij is equal to 0 if I equals j. And if I is not equal to j, well, then we get two possibilities. If I is not equal to j, there are essentially two things to consider, A12 and A21. Now, A12 would be determinant of E1, which is 1, 0, E2 is 0, 1, it's just the identity matrix, and this would be 1, while A2, 1 would be the first column would be E2, which is 0, 1, second column would be E1, 0, 1, 1, 0. So, this would be minus 1. So, what I end up getting is, now going back to this, I end up expressing the determinant as, so there are four there are four terms in this sum. I can vary from 1 and 2, j can vary from 1 and j varies from 1 to 2. So, but amongst these four terms, I already know that A11 and A22 are 0 because of this, and then A12 is this. So, it's E1 star tensor E2 star minus A21 E2 star tensor E1 star. So, we can write the determinant can be written like this. In fact, we are going to come back to this again when I talk about alternating tensors or multilinear forms. Now, before I do that, so let's linear transformations. And pullbacks. So, here the situation is as follows. So, let's say a linear transformation from V to W, and I want to look at, so far I have been using this notation L. If I want to look at multilinear maps on V, I'll have to take certain copies of V, which the case we have been considering involved different vector spaces. Here now I'm going to assume all vector spaces are in the domain are the same. So, I'll be looking at V cross this space, so k times k entries of these. So, this I'll denote by L superscript V. So, and of course, V can be any vector space, same thing for W. So, now what I want to talk about is that when I have a map of the underlying vector spaces, I can get a corresponding map from the space of multilinear maps on W to V. So, define T upper star called the pullback map. This is going to take LKW, it gets reverse. T is from V to W, but this will take LKW to LKV, is defined by so the input for T star, T upper star, is going to be an element of LKW. Let's call it alpha. And the output T star alpha is supposed to be an element of LKV. So this should act on V1 all the way up to Vk. And I define it to be, and here, so I started with alpha in LKW. So I define it to be alpha of T of V1, T of Vk. So this is called T star alpha. It's called the pullback of alpha by T upper star. So then small proposition. Right, before I do that, yeah, okay. So I can just state it as a proposition. Proposition. Now notice that I've written, what I've done here is I just said what T star alpha acting on V1 up to Vk, I come up with a number. So this, once I give, we are given V1 up to Vk, this right hand side here is a number, but what I really want to know is whether T star alpha is an element of LKV. So that's in fact true. That's in other words, it's multilinear. So first thing is if alpha belongs to LKW, T star alpha belongs to LKV. This is extremely straightforward, using the fact that this original map T was linear. So I won't prove this. And the second thing is that these spaces, these sets LKW and LKV are themselves vector spaces, as I remarked earlier. And I have a map between two vector spaces. So one can ask if whether T star is linear. Again, it's very easy to check that T star is a linear map from this space to this space. But in fact, one can say more. So these are elementary observations, but since we know that LKV, we proved that this is actually equal to V star tensor V star K times and same thing for LKW as well. One can ask what this T star does to tensor products. So the second proposition is that T star LKW is W star tensor, again K times. So if I take an element of W star tensor, W star is not something of the form which is it's a linear combination of tensor products. It may not itself be a tensor product, but I can look at something like this T star alpha 1 tensor alpha K is equal to T star alpha 1 tensor T star alpha k. These are one forms. This again is just a matter of going by definitions. So I will skip this. And moreover, this and equally important is this composition law for T star. So if I have three vector spaces, W, V to W to X, let's say. So and this is T and this is another linear map S. One can of course compose S and T and get a linear map from V to X. And then one can take, so let me write it in a different way. So V, W, X. So this is S and this is T. So here I have S composed with T. Now when I look at what the action on LK, so I'll have to go in this way. LKW, LKX, then LKV. So T star goes here and then S star goes here and then this is S composed with T star goes here. The question is whether going like this, S star and then doing T star, it's the same thing as S composed with T star. And the answer is yes. So S composed with T star, we have S composed with T star as T star composed with S star. Again, note that this order of composition gets reversed here. This was S composed with T star, but this has become T star composed with S star now. And another important property is that if I have the identity map, this is actually quite trivial, but one should mention this. These two, the 2 and 3 sort of go together. Together they make up what is called the functorial property of this pullback. So if I have the identity map from V to V, then this I star from LKV again to LKV is also identity. All of these things are extremely straightforward to check. No, other than the definition, nothing else is needed. So we'll move on and I'll leave it to you to check that these things are true. Now I want to talk about two special classes of multilinear maps: symmetric and alternating forms. So perhaps this is a good time to stop, and in the next class I'll begin a discussion of these things. Thank you.